Hey students, here's my second video on examples from chapter 30. I'll repeat what I said in the first video that examples 23, 28, and 59 were done in the video lecture number 21, and at a time stamp of 00, 30 minutes, and 55 seconds is where 23 starts, and it does those three. And so then in that second video, I made these three, which would be 31, 38, and 41. And I realized that, and here's the 41 I just completed, that I didn't do the part B. So this was just the part A. So let me begin this video by doing 41 part B, and then I'll jump into these other three, and that will be complete 9 examples from chapter 30, a real hard one here. Okay, so here is 41 where we did A. We talked about the flux. Here's the sheet we were looking at, and so we did this. It says calculate the flux through a surface of the disk, and then it gave it this radius at the position perpendicular to the end of at a position perpendicularly to and centered on the axis of the solenoid as shown in figure A. And so we were looking here at this figure. And so now B has a slightly different question. It says look at figure 30.41b, and it shows an enlarged end view of the same solenoid. Calculate the flux through this blue area in this annulus ring with an inner radius of 0.4 and an outer radius of 0.8. So in figure B here, you can see that this radius, 1.25 centimeters, is the solenoid. And so using the green here, the magnetic field is everywhere and constant inside the solenoid. And so let me kind of represent it that way. And maybe to make this one go a little bit faster, I'll go back to our discussion of part A, where it says, okay, when you go to calculate the flux, which is a dot product between the magnetic field and the area, the way it is aligned, the angle is 0 and the magnetic field is constant inside the solenoid. And so I'm pretty sure that's why the author had us working on a solenoid. And so then it just becomes B times the area for this simple case. And that's what we have here. Of course, in A, we said that it would only be relevant where there was a magnetic field, so we didn't do the whole area of the disk, and I think that was a big, important part of 41A. And then 41B is just to say, well, okay, the flux would be the same, again, everywhere in this blue area, and then we just got to talk about the area of that blue annular ring. Okay, so B really boils down to this. The flux is B times the area. And then B we did earlier on as 0.0151 Tesla. And the area would be pi, and I'll call it the bigger radius. Let's see, how does he doesn't really label it, but I'll go R2 squared minus the smaller radius. And so if we call this right here R2 and the shorter one or inner one R1, then this first term is the area enclosed by R2, and then of course we're going to subtract off the area enclosed here, which leaves just the blue stuff. So 0.0151, maybe even I'll factor out a pi, and then it just becomes R number 2, which is 0.008 squared. That's the 0.8 centimeters, and written in meters, minus 0.004 squared. And then it's a pretty just straightforward calculation. Okay, so let's finish up B before we get really into this video. So 0.008 Wait, is that radius or diameter? Inner radius of point, yeah. Okay, and outer radius. Okay. So that would be squared. And then subtract 004 squared. All right, then whatever we get, multiply that by pi, and then multiply that by 0.0151, and we get a flux of 2.28, and again, Tesla times square meter, or if you want to call them Webers, that's great also. All right, so thank you for bearing with me and letting me finish up 41 that I forgot to do when I was doing that video. Let's then jump into the other ones. And number 47 is the first on my list here. So maybe I'll put number 47. So 47 says we have a very long, thin strip of metal of width W. So we got a nice little picture here. Carries a total current of I, so there's a little I, along its length as shown in the figure. Find the magnetic field at this point P in the diagram. The point P is in the plane of the strip and is a distance B away from it. And of course, that's a diagram away from the edge, not from the center or not from the far edge, but the close edge. Okay, so this one, like a lot of all these, is we didn't really actually do anything like this in the lecture in terms of the Ampere's law, but we did do a long straight wire. And so what I'm going to do is write down the equation for a long straight wire, and maybe I'll just mentally think of it as this strip as a summation of a bunch of wires. And so I guess I would write it this way. I would say, okay, so the magnetic field from the strip, I might even call it a plate, is equal to the summation of the magnetic field from a bunch of long wires. And that's kind of the logic here that I want to kind of work with here. And so if I maybe begin by taking this equation for a wire and think of this small little strip, whether it's the closest one or the further one, I'll just say it's made up of a microscopic amount of current, let's call it DI. And so there's this microscopic amount of current. And then, of course, how far away is it? Well, it depends which strip we're talking about. The first strip that is closest is a distance B away, but the other ones are further away. And so this R, the distance away, is gonna vary as I get up the magnetic field. And of course, I better be careful. These are actually vectors. You got to add them up. But it would look, I guess, something like this, that then B of the strip being a summation of a bunch of B of the wires. And they made it kind of easy on us, if you will. In one sense, I mean, it's not an easy problem, but I think it didn't elevate to a magenta color like 49 is, because these fields are all in the same direction. What I mean by that is if I take my right hand and do right hand rule number 2, and I pretend to grab one of these strips, it doesn't matter which one, but I'll kind of just pretend to grab it. Maybe I'll make my pen kind of representing that strip. And if I grab it, you'll see that the field comes around. And then over here at point P, it would be pointing up. And that would be true for any of the strips. Now, the strips that are further away are going to be smaller in size, but they all point up in a Z direction. And it's, of course, a lot easier to add a bunch of vectors that are all in the same direction. You just have to, get their magnitude and add them together, just like scalars. And so that's why, like I said, I think this one was nice to us. And next one's going to give us a little more bang for our buck, if you will. I'm going to really make us think about this deeply. Okay, but here, again, if they're all pointing up, I could come over here and, just not even worry about the vectors. And so instead of putting a vector sign and adding them, I can cross it off and just say, I'm going to take the magnitude of the one from the first wire, the second wire, the third wire, the fourth wire. And, each wire has the permeability of free space times a small amount of current, and then the distance away. You might even say, put it right in there, in the limit that the small amount of current goes to 0. In fact, I kind of already did that right here. Maybe I should have called this just a small amount to distinguish it from the total amount. So the total amount is I spread out over the whole strip. But here we're going to be saying there's just a small fraction within one little microscopic strip. And we're going to take the limit as the strip gets smaller and smaller. Therefore, the amount of current gets smaller and smaller. So we could then say, okay, so the field by the strip would then be an integral of mu naught di over 2 pi r. And so that's going to be my integration. And that is, I guess I'll say, like we did a lot of these in Gauss's law, the first part, and maybe one of the hardest parts of the 3 steps, is really taking what you already know and applying what I'll call, I guess, algebra in the limit, so calculus, and getting an equation, because you won't find this equation per se anywhere in the book. You just are here to figure it out on your own. Maybe not. Maybe they did this. I'll have to, after the video, go and look up. They may have done something like this, but the potential is that they didn't. The potential is that they expect you to visualize it as a bunch of wires. We definitely did a wire, and the sum of a bunch of wires make a strip. Okay, so this is going to be my integration, and that, like I said, is, I'll call it major step number 1, coming up with that equation. But number 2 then is to somehow convert a di into, say, a d, and you can kind of see that I'll be adding up along the y-axis here, and so each little microscopic wire that is going to be summed up to make the strip is spread out on the y-axis. And so I have to do a conversion somehow. If I use some math fancy words, I'll have to do a transformation from an integration of di to an integration of dy. Okay? And probably the best way to do that is to come back here. Did they say current was spread out evenly? A very long, thin strip metal carries a current I along its length as shown. Find the magnetic field at point P. Okay. They didn't explicitly say that the current was spread out equally, but on the other hand, they didn't give me any other kind of distribution. So kind of the default here is that it's uniform. And here's why I do that. Because when something is uniformly spread out, you could take the whole current and divide it by the whole width of the strip. That's the same as a microscopic small piece of current over the width of that small little piece, okay? And so in my case, the small amount of current, I will say, is di. That is, thinking of this small little strip, there's a small amount of current, and it's spread out in a small width right here of dy. And of course, the whole current is I, and the whole width is W. And so if we go whole current divided by whole width times a small width, that gives us the small amount of current. That kind of makes sense here, right? This is the density of the current times that small little length is going to give me the small little current that is in that long strip of wire. And so this is my transformation from a di to a dy. And then this is the extra factor. So I can call that a Jacobian of transformation, if you will. Maybe I'll just call it a factor. And then say my di becomes I over w dy. Yeah, you'll notice I skipped over the r, because the r is the distance away that it is. We can use the grid they give us. But I actually think it's a little easier. I'm just debating. I don't really want to use the grid here where they gave us. I just want to say the distance away would be some variable, how far, this direction. And then it would start at B, and it would continue on until I got to B plus W. And then that would, on the other hand, if I use the distance away, I guess it would be, where you are on the grid. And then I got to take this and minus the distance. Yeah, let me go. I hesitate to get away from his grid just because, I don't want to lose anybody in my explanation, but I think in this case we're better off. In other words, I'm going to do this. I'm going to say, let's take a cross-section of that strip and then say this is some distance r. And so why don't I leave this as an r, and then you'll see that the first little strip does start at a distance b away, and the next one gets further and 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 further, and eventually, here's the width of it, it gets to being b plus w away. And I like that. Of course, now that means I really need to come back up here and call this a small current over a small width dr. And so this is a dr, and then this is a dr to make it kind of match. But, yeah, I think it's worth kind of changing our grid then for that. All right, and then so if you kind of look at this, what doesn't change would be the total current, the 2 pi, and then the width. And so you just have the dr over r with the limits of b to b plus w. And so if I head off here to page 2, see if we're going to come back to page 1, probably not. I can just put here mu naught I over 2 pi w, and then this integral is a natural log of b plus w minus the natural log of b. And maybe one last step, taking advantage of the property of logarithms, I can go ln of b plus w over b. And I don't really like it this way, but I noticed in the author's solution, he likes to then separate these and put it as 1 plus w over b. And same thing, and that's fine. Actually, it has its pros and cons, like each of them do, and there's something nice about this. But either of those, I think, fits the answer, what he's getting for in terms of symbols. What is the magnetic field there? All right, well, like I said, hopefully that one wasn't too bad, but it was a nice exercise in some calculus and also some vectors, although they were vectors in the same direction. And as I alluded to, that changes here in number 49. And 49 probably needs some kind of model or something here. Because it says here, a thin copper bar of length 10 centimeters. And so I think they're looking here, is supported horizontally by two non-magnetic contacts. The bar carries a current of 100 amps in the negative X direction as shown. And so here's the author's grid, X and Y and Z. And current number 1 is going, looks like down this, I'll call it a bar, but then it goes across, well, I should call that a rod, and then what he calls the bar right here. And so it goes across this, this bar, and then on through. And so that metal bar is sitting up there. But here's what's interesting, is that it, gives some dimensions. It says that the bar here, so at a distance of h equaling a half a centimeter below one end of the bar. And so there it is, below the bar. So this rod here, number 2. A long straight wire carries a current of 200 amps, I2, in the Z direction. So there's my grid. Determine the magnetic force on the bar. Ooh. Now, clearly, you can see that we have a current, number 1, and it's in a magnetic field, which is created from current number 2. And so we've done a couple of problems where, we had, I think this was section 2 of chapter 30 here. We had like 2 wires that carrying current maybe in the Z direction here. And there was, a magnetic field, let's say, created by this one. And so we've got these circles. And so number 2 is a current in a magnetic field created from number 1. Or maybe I should call it the other way around. There's a magnetic force on number 1 created from current number 2, because that's what we're going to be looking at. We're looking at how much force is on this bar. And so we'll say, okay, how much magnetic force is on number 1, going with current number 1, coming from current number 2. Okay, so maybe drawing a cross-section of just maybe the relevant pieces might be important here. And so I'm going to draw a cross-section of this copper bar, and so my drawing is here. I won't bother to draw how it's being held up or how the current comes in, because I just want to focus on this bar. So this bar has a current, which we are calling number 1, which is 100 amps. But you see, it's going to be in a magnetic field from number 2. So number 2 is in the Z direction, and so a cross-sectional view would be coming at you. So maybe a little distance below, there would be this current number 2 coming at you, coming at the screen. So I'll put a little dot right there. There's current number 2. And it then is going to make a magnetic field that has an impact, a force on there. And that's what we've got to talk about here. Now, they did give me some dimensions here. It says at a distance of a half a centimeter below one end of the rod, a straight wire carries a current of 200. They didn't give me the dimensions of this straight wire. And so I'm going to imply here that they're talking about the distance here, h, half a centimeter from oh, and I should have put maybe the center of this strip to the center of the wire. And I think it would be much harder otherwise. But I don't know what else I could do if they, wanted me to somehow incorporate and mean this was to like the surface of this wire. Well, then I need to know how far I am from the center, because going back a problem, you might remember the magnetic field from a straight wire has to do with the measure from the center. So, bummer that the problem is not written at quite as clear as I'd like it to be, but that happens a lot. And so it's a hard enough problem without worrying about the actual size of the strip or the size of the wire. So I think that's what the author is implying here. Don't worry too much about these dimensions. This is going to be hard enough. And so like any problem, conceptually, you just want to start off first. So if I go ahead and say, okay, I'm trying to find the force on this strip, and to do that, I need to know the current of this strip, the direction of the current, and the strength of the field, and the direction of the field. And the field comes from number 2. So let me start there. Let me pretend to grab wire number 2 with my right hand. I'm going to do right hand rule number 2. And so maybe I'll have my pen pointing up toward, or out towards you on the screen. And I'm going to grab this. And so I would have a magnetic field that's, at least at this end of the bar, would be the same direction. Strip, the same direction as no, he calls it a bar in this one. The same direction as the bar, which would be the negative x-axis. But as you might be able to see, as you get further away, the field changes direction. It also changes strength, by the way, because you're further away. But hopefully that one's obvious. And maybe I should have put one right here in the middle. And so a circle. So right here would be this way. And so we're going to have a magnetic field that, again, keeps changing in terms of its magnitude, but also in its direction. And so this last magnetic field, out of looking at all of these, is getting pretty close to being straight up. Obviously, it wouldn't be exactly straight up. You'd have to be right here. But since we are talking about an overall length of 10 centimeters here, and this bar is only a half a centimeter up, this is almost straight out. But not quite, that's okay. But the biggest point is just conceptually seeing that, wow, this is going to be hard, because the strength of the field and the direction of the field keeps changing at every point along this strip. All right, well, maybe you remember this nice little equation that we worked out that says if you have a current and a small little section of that current, and you cross it with the B field at that small little section, you will get a small little force. And so if you wanted to get the total force, you would just add it up. And that's what I want to do then. I want to add them up. Okay. Now, adding them up, and maybe I should have pointed out, this came from force equals a moving charge in a magnetic field has a force on it. But let's not go all the way back to here. I think the author wants us to, begin this problem right here after he derives this step to here, and now wants us to do this integration. Okay, so let's talk and come here from this picture, because I have a cross product. This is the direction of the current, and this is the direction of the field. Now, one thing about this bar here is the current is always in the negative x direction. So as I look at each section of this bar, I can safely say, okay, this ds is always in the negative x direction. And it's listed first in my cross product. So if I take my right hand for right hand rule number 1, I'm going to always put it in my fingers in the direction of the negative x-axis. So then if you remember, you're supposed to then rotate your wrist until you can close your fingers towards B. And so maybe if we look at this far one right here, I would do something like this. I put my fingers first in the negative x, then I'd rotate my wrist so that I can close towards B. You're not quite 90 degrees, but almost. But notice my thumb is going in. And so I would have a force that would go in. I guess that would be the negative z direction. And if I do that anywhere on here, it's always inward in a negative z direction. Now, the angle keeps changing, and the strength of the field keeps changing. And so because of that, I'm quite sure the individual microscopic forces at each point change. And so, again, this is probably still not going to be easy, but I like what I see right now, where the force is always in the z direction. And so adding up forces that are in the same direction are the easiest vectors to work with. That was a comment we made, I guess, back in this 47 one, where the magnetic field was all in the same direction. So we just added it up. And so in this case, this bar magnet is going to be pushed, each little piece is pushed backwards. And it'll be interesting to see how they compare, because, this far piece is getting closer to 90 degrees, which when the angle increases between these two, the force grows, but it also is getting further away. So it's going to be hard to say, is this little microscopic amount of force bigger than some of these other ones? And who knows, maybe it gets bigger for a while and then smaller. Either way, we're going to add them all up and eventually get the total force. I suppose a harder problem would be adding them up and doing a torque. Because I can see here that this metal bar, then, if it was kind of free to slide, would be pushed back in the negative z direction. But it'd be kind of interesting to see if, as it's getting pushed in the negative z direction, does it rotate? And I would be surprised if it didn't. I'm not sure which way it would rotate, but it's going to rotate as well as being pushed back. And that would be a fun problem to do. But since they're not asking for it, let me not do it here on video. Maybe I'll have some entertainment time afterwards and go, what, maybe I'll calculate the torque on that to see not only does it get pushed back, but whether it rotates counterclockwise or clockwise as it gets pushed back. But back to just the force. So I'll say it again. We're very lucky here in this cross product to realize that every single cross product, so current in the negative x direction, across the field is in a negative z direction. And so I can drop the, vector here and just say I'm going to just add up magnitudes. Okay. So because of that, I'm going to then have the I, the little bit of length of the current, times the magnetic field, times the sine of the angle between them. And just to remind you then of a cross product, A cross B, okay, is, well, the magnitude of A times the magnitude of B times the sine of the angle between them. And so really here, this is the magnitude of S, the magnitude of B, and then the angle between them. And I need to just be a little careful with my calculus, because I will probably then change this to a dx. And of course, then I can ask myself, am I going to add up from here out to here? And I think that's best, because then my little bit of current, although points in the negative x direction, I want its magnitude, and so that's just a dx. There is no negative to worry about when I do that cross product. All right, so that's why I wanted to point that out, just in case somebody was looking at this going, okay, now should there be a negative because ds is in the negative x direction? Yes, but a cross product is its magnitude. Okay, and then the magnitude of the magnetic field is given by this equation. But let's be careful here, because I got a current here and a current here, and this is actually the current on wire number 1 that is coming from the magnetic field that is created from number 2. So this is a number 1, because this is the current in this bar, and then the bar is sitting in a magnetic field that's created from number 2, and so that's why that would be current number 2. And then this R would be something like this. It would be, okay, well, how far are you? And so this R looks like I'm going to have a little bit of a Pythagorean's theorem going on here to figure out how far it is, because it would be this distance, which we're going to call the x distance, and every little strip is a little further in R, but the vertical height is always the 0.005 if I put it in meters, because remember it said half a centimeter. Okay. And we also have this sine of theta. This is, I think, going to be the hardest part of this problem. So let's keep talking. All right, so let's see. So I've got this integral. I've got this current I1. I've got this dx. I've got the mu naught. I've got I2. I've got the 2 pi. And then let me go ahead then at this r right here. And this r is this distance away. So let me call it x squared plus 0.005 squared square root. Okay. And so that is how far away we are. Now, theta, it's going to take a little bit of looking at what we mean by a cross product. And back to our picture. Theta is the angle between the two vectors that are listed. So ds is going that direction, and b is up at an angle. And so if you'll let me, on this picture right here, extend the b field a little bit longer, then the theta is this right here. It's really the angle between the horizontal and this magnetic field. And here's why this is, I'm trying to think of maybe the best way to go with this. If I extend this line out and the magnetic field out, then let's see, this angle here would also be theta between the horizontal and going down. Okay. maybe that wasn't the best way to go. Sure, why not? Because then this one tucked inside here, the magnetic field and the vertical, right here, would be 90 degrees minus theta. It'd be the complement. Which then, this angle, which is then part of this red triangle right here, would be the complement of this one, meaning we're back to theta. And that's what I was trying to get. Maybe it would have been easier to go this way, because then this would have been the complement and then the complement of the complement. But I was trying to figure out which one of these two would come out to be theta, because I'm looking at this triangle, and so when I have sine theta, I want to know which one is my theta. So it looks like this one up here in the red triangle is the theta. And so sine means the opposite, so that's the x value, x, over the hypotenuse, which is x squared plus 0.005 squared to the 1/2 power. And then, fortunately, I like what I see. This is going to be a pretty straightforward integral. So I think we've done the hard part here, because now, as I look at this integration, I have changed everything to d to x's. Everything else is either a constant or an x. In other words, across the top, I have mu naught, current 1, and current 2 right here. And so I have an integral of x dx here. And in the bottom, I've got the 2 pi from here. And then these two are the same thing, right? This is the first one that came from r, the distance the magnetic field goes away. And the second identical factor was coming from the sine of the angle. And so this would be x squared plus 0.005 squared to the 1 power. And you'll see that this numerator is the derivative of this, or the chain rule of it. So this is a nice little u sub. So we don't have to do one of our harder substitutions. We can just do a straight u sub for this. All right, so let's see. Shall we call this page 2? And so we've got our mu naught I1, I2 over 2 pi. And I have an integral. Now, maybe I should have commented about the limits of my integration, because they did say that this bar magnet started directly over it. So in my diagram, directly over it right here is x equals to 0. So we're going to start at x equaling 0. And continuing on until we get to the end of the bar, which is 10 centimeters. And so I'll write it as 0.1. And so that'll be limit of my x. But I probably should write u as x squared plus 0.005 squared, so that this bottom becomes a u, and du becomes 2x dx, and then moving the 2 to the other side, x dx, so that's what I have right here, x dx, is really a 1/2 du. And then maybe taking this 1/2 out to here would go mu naught I1, I2, I guess that's a 4 pi. And the integral of du over u is the natural log of u. And of course, those of you who know me, sometimes I'll put the limits of u, but most of the time not. because before I put the limits, which I already had the limits in terms of x, I'll just go ahead and put my x's back in there. Although this would be real easy to get the limits of u. But here's mu naught I1, I2 over 4 pi. And then ln. And then in place of u, I'm going to put x squared plus 0.005 squared. So that'll put us back to the x's when I substitute what u is. And then, as we said, from 0 to point... Oh, point... Wait. Did I... So half a centimeter, yeah, to 0.1. Okay. Yeah, so this is quite a bit bigger, right? 20 times bigger. Okay. Okay, so if you'll let me kind of combine those, that's 10 to the minus 7. And then my current, number 1 of them was 100, and that was number 1, so this is a 100. And current number 2 is 200. And then I would have ln, and I guess I'd have 0.1 squared plus 0.005 squared minus, and I'll take advantage of the properties of logarithm, 0.005 squared. And that should be then the force. And you can see, because of the permittivity of free space, or permeability, excuse me, of free space, that's going to be pretty small here. Okay, so here I have 0.1 squared plus 0.005 squared. Nice. Then I will divide that by 0.005 squared. Nice. And so that's 401. And so let me take the, where's the natural log? Natural log of that last answer. So this is roughly a 6. So I'll go 6 times 200 times 100 times 1 times 10 to the negative 7. And so a force of 0.0120 newtons. So not much, and probably not even worth considering it moving. It would kind of depend on how much friction there is here, but it seems like it's not going to move unless you took extra effort to significantly reduce the friction so that it could move here. So these magnetic forces, even with 100 and 200 amps, are small. Maybe that's another lesson to learn in this one. So, wow, that's a great problem. Good problem. Hard problem. All right. And the third one. Oh, I had a yellow paper here. So, go ahead and grab some more yellow paper. All right. And the third problem for this video is right here. But it's got a nice little learning lesson. I'm not sure. Well, maybe it does deserve to be magenta. Because there's a little trick to it that is worth talking about. But once you see it, it's kind of like when you did center of masses. In fact, let me just kind of review a little center of mass. Maybe you remember doing something like this. Maybe the easiest one you did was to take a rod and say, okay, where's the center of mass? And this one was so easy. You could actually set up the summation of all the masses, if you will, and say, you know, X at the center of mass is 1 over the total mass, added up the position of each little mass. But if you kind of put your grid right here, you would see that you were going to go, you know, from a negative L over 2 to a positive L over 2. And you would have a symmetric limits to your integral when you do it over an odd function, and so that comes out to be 0. And so we probably didn't do too many calculations. It was just so obvious where the center of mass is on a rod. But if you had something that had more mass, that got a little bit harder, because if this part of the triangle is A and this is B, you'll see if you kind of cut it in the middle, A over 2, there's a lot more mass to the right than the left. And so when you perform this integral, you find out that the center of mass right here is a distance from the, I'll call it right angle corner, of 1/3. Or you could go this way and get 2/3 A. And then fortunately, when you were doing a triangle back in Physics 121, you probably also then realized that there's no point in doing the y-axis, because if you just held up the triangle kind of in the same way, like this, and then this is B, you're just going to get that same thing, B over 3. So you could then say that in this direction, the center of mass would be B over 3. And so the center of mass of the triangle would be right there. Now that's all good, and I haven't really got to the part I wanted you to see, but what if then you had say a second triangle? And so you had your original triangle, AB, and you had a second smaller triangle, DC. You, instead of integrating all of this, would say, well, let's just take the center of mass of the first triangle. And so in terms of a coordinate here, from this corner, would be A over 3 and B over 3. And then take the center of mass of the other triangle, which would be B. Oh, I'm going to call that B. Let me call that C and D. That'd be better. So that would be C over 3 and then D over 3. And then you would just treat it like 2 point objects, and then no calculus is involved, and then you would just find the center of mass of your 2 triangles. But the real hard one, or at least the hard one on the surface, is the one when you have a triangle, A and B, and then you cut off a triangle. So you eliminate that and call that a distance of C and D. What did you do then? And in case you have forgotten, you, of course, said, okay, well, the first triangle would have a coordinate of A over 3 and B over 3. Okay. The second triangle, although it's not really a triangle, but if it was a triangle, okay, if it was a triangle, it would have been just like we talked about. Here, the center of mass would be a C over 3 and a D over 3. And then you would just treat it as 2 objects, and you would do that, mass 1, position 1, plus mass 2 times position 2 over the sum of the 2 masses to get the center mass of the combination of the 2 triangles. So again, that's what you would have done here. But kind of a tricky approach here is to say, what if you think about this second triangle not so much as a triangle with mass, but a triangle with negative mass? Because you can kind of see that if I had a full triangle, this would be the center mass of a full triangle. And if there was such thing in the physical world as negative mass, I could make a triangle of this size, CD, with negative mass and put it in there. And so when you combine the mass from the original triangle and the negative mass from this imaginary triangle, you get 0, and that's what you get when you cut it away. And so an object that looks like this it's not too bad, even though it's cut and doesn't look like a triangle. You can find out what its center of mass is by instituting this idea, that doesn't really exist in the physical world, but a negative mass. And we're going to do the same thing here. Watch this one. 67. A long cylindrical conductor of radius A, so this is this big one, has 2 small cylinder cavities of diameter A through the entire length as shown. Okay, so they just show a cross section, but it's a real long wire. A current of I is directed out of the page and is uniformly distributed through the cross section of the conductor. Find the magnitude and the direction of the magnetic field in terms of mu naught and I and R and A at points P1 and at points P2. And so here's what I'm going to do. I'm going to view this a lot like a triangle of negative mass. I'm going to say that I know how to treat the magnetic field from a long wire. That's the discussion we had on number 47. This is the equation. So why don't I think about this as being made up of 3 wires? One solid wire that is carrying a current of I1 this way. And then another wire embedded inside of it carrying a current of I2 in the other direction. Because if you have a current, I'll call this towards my left, and another current towards my right, and they're the same density, not the same amount, because remember, current 1 is spread out over a much bigger surface than this one. But if they have the same density, there would be 0 current in this spot. And that would be equivalent of having a hole. A hole has 0 current. That is our discussion back here about a hole having negative mass. If you put real mass with negative mass, you get 0 mass. That's a cutaway. And that's what I'm going to have here, a cutaway. And so I will have current going to the left and an equal concentration of current going to the right. The net current in this area then is 0. And so what I can do is treat these as a field made by the big wire and then the small wire. Of course, I need to do this another time. I'll call it current number 3. I think you can see that 3 is going to be the same as 2. I'll just write it as 3 to get us started. But again, to get 0 current here, I'm going to think of this as current going to my right with the same density as the current from the big one going this direction. Okay, so let's do P1 first. All right, so if I say, what is the magnetic field at P1? I'm going to say it's the field from wire number 1, wire number 2, and wire number 3. And wire number 1 is the big one without any holes drilled out. So it would be mu naught times I1 over 2 pi, and the distance away from the center is what is meant here by R. And so that's the magnetic field from number 1. Now, I need to add it together, and I got to be careful. These are vectors. They may or may not be in the same direction, so I don't know if I have to add them or subtract them or do Pythagorean's theorem. And so maybe I better talk about this first one. If the current is coming out towards me, as I guess I didn't put a little arrow here, But I would take my right hand with my thumb towards the screen here, and this would make a magnetic field pointing in, if you call this the x-axis, this the y-axis. This field would be pointing in the negative x-axis from this big wire. So I don't know if I want to put a negative I hat just to put a direction there. But I have a feeling that they're going to be in the same direction for this case, and they're going to get harder on me on B. But let's see. So let's talk about wire number 2. So wire number 2, like I said, is really me imagining a current going the other way with the same current density. And so I'm going to go ahead and say, all right, current goes this way. And using my right hand rule number 2, I would get a field in that direction. And by the way, as long as I'm here, let me do wire number 3 also, because it's going in the same direction. Now, it is further away, but as I put my thumb in the direction of the current, it's going to go in the x direction also. And so that would be helpful in the sense that this is an I hat, and the other one is an I hat. And so these two, I'll call them holes, which I'm thinking of them as current going the other way, because right, current going this way and equal density going the other way, would balance off and I'd get no current. So that is not quite the same direction, but at least they're opposite directions. And so 2 and 3 I'm going to add together and then subtract it from number 1. And so let me keep going here. So I've got a mu naught I1, I got 2 pi r, and I'll have my negative I hat. Okay, so the field from this one would be mu naught times current number 2 over 2 pi. And R is going to be a little different. Remember, R is measured from the center of the wire. Okay. And the center of this wire is not down here on the x-axis. It's off a little bit. I guess the whole diameter of the wire is A. This radius is A over 2. So this would be R minus A over 2. And I hope you kind of see the same thing for this third one. It's mu naught, current number 3. And although I put number 3 here, would it be okay if I just put current number 2 also? Now, it is further away because the center of wire number 3 would be the R, and then I'd have to add an A over 2. So this would be R plus A over 2. So if I combine these together, I'm going to have a mu naught I2 over 2 pi. And then I'm left with a 1 over R minus and 1 over R plus. And so that is in the positive I hat direction. And maybe if it'll be okay with you, I'm just going to say, okay, look, I convinced myself that the field is only in the x direction. So let's just focus on that and drop the I hat. So I've got to be careful with my negative here. I might even get a common denominator here. So this would be mu naught I2 over 2 pi. And this common denominator is going to be R minus A over 2 and R plus A over 2. And so that means, oh, wait a minute. Why did I put a negative here? Yeah, okay. This should just be a plus because they're, we said they're in the same direction. Okay. So this would be an R plus A over 2. And then this one would be an R minus an A over 2. And then this one would be a minus mu naught I1 over 2 pi R. Okay. Now, I guess I will simplify that a little bit, but that's not the big piece here. But this is a 2R, which would cancel a 2. And then I would have this R minus A and R plus A. Okay. Now it's going to get, I think, a little bit harder because we are asked to get current 1 and current 2, but notice those are things I invented along the way. They're saying the total current is what flows in this, I'll call it this weird volume here. So the current density really is the total current divided by where the current is spread out. And it is spread out at pi A squared minus pi A over 2 squared twice. That is the area that's in kind of this tan color, because I have the area of the big piece, okay, and then I subtract off the holes. And I'm pretty sure it says here, a current I is directed out of the conductor. Find the magnitude. But it carries a current of I. And it's directed out and uniformly throughout the cross-section of the conductor. All right. So this would be I over, and we got this pi A squared minus. And so this right here would be a 4. And so this would be pi A squared over, I guess that's a 2. And so that would be a current over, if I have pi A squared, that would be a plus 1/2 pi A squared. And so the current density is 2 times the total current divided by pi A squared. And you might be able to have seen that from the beginning, because when you cut out 2 circles here, you're cutting out half the area. In other words, the current density would have just been I over pi A squared if they hadn't cut out any holes. They cut out half the material, so the density goes up by a factor of 2 for that same amount of current. So there's the current density. Now, here's why I say that. Because I1 must be the current density times its area, pi A squared. I2 would be the current density times its area, which would be A over 2 squared, or pi A over 2 squared. Okay. And so putting this in here, you can see that the pi over A squared is going to cancel off. And so, again, not a surprise that current number 1 is really thought of as twice the current, because current number 1 would be like this whole thing where everything was filled in, but we're kind of double counting the amount of current, because when we think of it as a solid piece, we're counting current for there. And that those little circles are half the area, so twice it. And same logic here, that this, to get the same current density, we have this 2I, and then we've got this pi a over 2, and then we'll have a pi a over 2 over 4, and the pi a over 2 and the pi over 2 will cancel off, and you will end up with 1/2 I. And again, hopefully that kind of makes sense, because each one then represents a half current. So the current going this way, I1, is 2 times the total current. And then the negative current is a half each. So when you put the two together, that's 1. And so 2 currents going that way and 1 coming back make a total of just overall 1 current. Okay, so then knowing these, let's put them back into this equation. Okay. All right, so number 2. Put it back here into this equation. So field in the x direction. Okay. Would be, and then right here, I'm going to go a negative mu naught over 2 pi r. And current number 2 is twice I. And then here I've got my mu naught, my 2 pi, that's from here. And then current number 2 is 1/2 I. Oh. You know, I'm sorry, I was looking at this line. Let me jump back down to that line. I didn't put a minus there. But minus mu naught 2I over 2 pi, okay, that one. And then mu naught times I2, which is a half, and then there's no 2 here. There's just a pi. Cancelled with that 2, so there is an R. And then it's over A minus, or R minus A over 2, and R plus A over 2. I suppose we could take this 2 now and drop it downstairs. That's kind of nice. Because once I do that, I begin to see that each term has a mu naught. Each term has an I. Each term has a 2 pi. And so I guess I'm left with negative 2 here, negative 2. And over here, I would be left with not I, 2 pi. Oh, there should be an R still here, and there will be an R over an R plus A over 2 and an R plus A over 2. Nice. And I suppose it looks like we have a nice common denominator here. And the common denominator would be R times R plus A over 2. minus, be careful there. And R plus A over 2. Now, that means here I would have a negative 2 times this factor, R minus A over 2, R plus A over 2, plus R. And I was kind of hoping something might simplify. But I don't see it. There's not going to be a R by itself. So I'm not sure I should keep going. And I'll take that as the answer. Wow, that was a good hard one too. Wow, and way over what I was hoping to do, about an hour, so I didn't lose your attention. But hopefully that was making sense, and hopefully that was helpful. All right, take care.